Ladies and gents, let's begin with writing products as sums and sums as products. So we are continuing Module 3. Please be open in your packets, follow along, and take notes as we go over Lesson 3. Let's begin. So for the opening exercise, we're going to solve the problem using a tape diagram, and we'll discuss what a tape diagram is. The problem states a sum of money was shared between George and Brian in a ratio of 3 to 4. And if the sum of money was $56, how much did George get? So we're wanting to use this tape diagram. And the tape diagram is mainly based off of the ratio. This is what it looks like. So for George, we have 3 rectangles. That's a tape diagram. We have 3 units for George. And for every 3 units we have for George, we have 4 units for Brian. So if we look at the total, combined between George and Brian, we have 7 units, and the sum of those 7 units is $56. So 7 units equals 56. If that's true, then using and simplifying that ratio, we can find how much it is for 1 unit. It would be $8. So next, after we find it per unit, we look at George. George has 3 of those units, so he has 3 $8 sections, so he has a total of $24. We take the 3 units, multiply it to 8, we get $24. Now, let's say we looked at the tape diagram and looked at each unit as x. Well, that means George would have 3x, Brian would have 4x. And in this case, what does x represent in the rectangle? Well, the rectangle labeled x represents $8. Let's look at example 1. For example 1, we want to represent a tape diagram for the following 2 problems. I would highly suggest trying this on your own just before you would see the answer here, so like pausing the video or anything like that, and then checking to see if you got the same answer. So representing 3 plus 2 using a tape diagram, we would simply have 2 units plus 3 units. So 3 squares next to 2 squares. We have a total of 5. If we looked at x plus 2, x is a specific distance. We do not know the distance of x. And that's okay. It can be as long as we need it to be or as short as we need it to be. And then we have the 2 units added on at the end. So that's roughly an idea of what x plus 2 would be. Example 1 continued. We want to draw a rectangle array for 3 times the quantity 3 plus 2. So remember, we're doing this for this type of problem, for one more basic, but it will become more algebraic once we get variables involved. So here, showing a rectangle array, we have a 3 by 3 by 2 set of squares. So 3 is our width, 3 is being multiplied to both 3 and to 2. Let's draw an array for 3 times x plus 2. Notice a very similar problem. The only thing that changed is instead of a 3 inside the parentheses, we have an x. So let's see what it looks like. We're going to still multiply the 3 on the left side to both x and to 2. But now that x, we're just showing that it's y. We do not know what x is. We do not have to know. It can be a small amount, a large amount, any amount we like it to be. And we're multiplying the 3 to the x and 3 to the 2. Determine the area of the shaded region. If we looked at the area of the shaded region, which by the way, for both of these, it'll be the same. We have 3 times 2, which would get us 6. So the area of the shaded region for both of these is 6. Let's look at the area for the non-shaded region. Well, the area of the non-shaded region is 3x. For this problem, we take 3 times x, we would have 3x. For the first one, we would have had for the non-shaded region 3 times 3, which is 9. So if we focused on this algebraic problem here, the area for each region, we have 3x and 6. Because 3 times x is 3x, 3 times 2 is 6. The distributive property. Distributive property, it can be written as the following. A times the quantity, b plus c, which equals a times b plus a times c. We're distributing a to everything inside those parentheses. We can have there be a multitude of terms in those parentheses and multiply a to every single one of them. So for all numbers a, b, and c, that identity is true. Just like what we had on the previous slide, this shows the distributive property. We're multiplying the 3 to the x and to the 2, and the products are being added together in the end. So we could write this in two different ways. We can write this as 3 times the quantity, x plus 2, or we can write it as 3 times x plus 3 times 2. They are the same. If we simplified, we would have 3x plus 6. And observe very, very closely how these are very, very similar. One is all algebraic, one uses both numbers and variables. Exercise 1. Determine the area for each region using the distributive property. So, let's begin. We have 11, 16, and 5. So, technically what we have is we have 11 times the quantity, 16 plus 5. Well, 11 times 16 is 176. 11 times 5 is 55. If we add those totals together, we can find the area of our region. Let's look at this diagram as broken up individual squares. 11 times 16. So imagine if we had 11 squares by 16 squares, we get 176. If we had 11 by 5 squares, we would have 55. So our total region area, if we were to combine it all, 176 plus 55, we would have 231. So is it easier to just imagine the 176 and 55 square units? Yes. It is much easier to imagine that, rather than trying to draw out all those lines. Example 2. Example 2, we want to draw a tape diagram to represent each expression. We have x plus y plus x plus y plus x plus y. We can make this a little bit simpler. Let's look at it visually. So using a tape diagram, well, the first one, we have x and y combined. We have x and y combined again, x and y combined again, and we have it 3 times. For part B, if we were to make a tape diagram of the expression that we are given, we would have x 3 times by right next to each other, so x, 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 y, 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 and we could add the sums together. Add the products, add the sums together. Example 2 continue. Part C, we have 3x plus 3y, adding the products together. So 3x's next to each other, 3y's next to each other. Here's another way that we could look at this. We could stack them. So instead of the x's being side by side, we could have the x's on top. So 3 times x and 3 times y. Part D, we have 3 times the quantity x plus y. Notice how this is extremely similar to that second way of writing part C. 3 times x, 3 times y, very, very similar. Example 3. Find an equivalent expression by modeling with a rectangular array and applying the distributive property to the expression 5 times the quantity 8x plus 3. So we need to figure out some equivalent expressions. Let's take a look. Well, first, let's look at the rectangular array. We have 5 times 8x, 5 times 3. Well, 5 times 8x, that's going to give us 40x. 5 times 3, that gives us 15. Here's how it would look if we were to write it out by hand without the diagram. So using the distributive property repeatedly. First, we distribute the factor to all the terms, meaning we're going to multiply 5 to 8x and 5 to the 3. So now we have 5 times 8x plus 5 times 3. We multiply. 5 times 8 is 40, so we have 40x. 5 times 3 is 15, so we have 40x plus 15. Let's look at exercise 2. For parts A and B, draw an array for each expression and apply the distributive property to expand each expression. After that, we're going to substitute the given numerical values to demonstrate equivalency. We want to show how they are still equivalent from the beginning to expanded form. That's what we want to show. Are they equivalent in the form they are now to the one that we're going to get them in? So for part A, 2x plus 1. 2 times the quantity x plus 1. So for part A, 2 times the quantity x plus 1. Using a tape diagram, the rectangular array, we have 2 times x, which is 2x, 2 times 1, which is 2, and we would add our two quantities together. So we now have 2x plus 2. And if we were to plug in for x, the value of 5, we have 2 times 5 plus 2 equals 12. For part B, we have 10 times the quantity, 2c plus 5, and c equals 1. So we're going to plug in c equals 1 just in a short bit here. First, our diagram. We have 10 times 2c, which is 20c. We have 10 times 5, which is 50. So we add our products together. We get 20c plus 50. If we plug in 1 for c, we'll have 20 times 1 plus 50, which is 70. So those show the numerical values to demonstrate equivalency. If we were to plug in 5 back into the original, we would have 2 times the quantity, 5 plus 1. 5 plus 1 is 6. 6 times 2 is 12. So they are equivalent. For part B, plug in 1 for c at the beginning. So 2 times 1 plus 5, that's 7. 7 times 10 is 70. They are equivalent. Exercise 2 continued. So for parts C and D, we're going to apply the distributive property, and then we're going to substitute in the given value. So let's begin. So first, if we were to distribute, we have 3 times 4 is 12. 3 times 1 is 3. Down our subtraction sign. So we have 12f minus 3. We now want to plug in 2 for f. 12 times 2 is 24, minus 3 is 21. Part D, we have 9 times the quantity, negative 3r minus 11. We want to plug in the value 1 for r. Well, first, distributing through 9 times negative 3, negative 27r. 9 times negative 11, negative 99. So our expression completely simplified, negative 27r minus 99. We need to substitute in the value of 1 for r. We do that, we get negative 27 times 1 minus 99 equals negative 126. Let's continue on to example 4. For example 4, we want to rewrite the expression in standard form using the distributive property. So first, we want to rewrite it as a fraction. So we change the division symbol to multiplication, and 3 becomes 1/3. Next, we want to distribute that 1/3 to both terms inside the parentheses. So 1/3 times 6x, 1/3 times 15. And if we simplify, 6 times 1/3 is 2. 15 times 1/3 is 5. We could look at that as 6 divided by 3, 15 divided by 3, and simplify our expression to become 2x plus 5. Now let's move on to exercise 3. We want to rewrite the expressions in standard form. I highly encourage you to try to do these on your own by pausing the video before reviewing the answers. So for part A, we have 2b plus 12. We're going to divide that by 2. Well, first we want to rewrite it using multiplication and a fraction. So 1/2 times 2b plus 12. So first we're going to multiply the 1/2 to 2b and then multiply the 1/2 to 12. When we do that, well, 1/2 times 2 becomes 1, so b. 1/2 times 12 is 6. So our final answer for part A is b plus 6. For part B, we have 20r minus 8, and that's all going to be divided by 4. So we want to rewrite this as 1/4 times 20r minus 8. So we have 1/4 times 20r minus 1/4 times 8. 20 divided by 4 is 5, so we have 5r. 8 divided by 4 is 2, so 5r minus 2. Part C, we want to rewrite. We then want to distribute. 49 divided by 7 is 7. 7 divided by 7 is 1, so 7g minus 1. Example 5. Let's write example 5 in expanded form. So, if we were to expand this, we're taking the 4, we're multiplying it to x, we're multiplying it to y, and we're multiplying it to z. So 4 times x is 4x. 4 times y is 4y. 4 times z is 4z. So the expanded expression, 4x plus 4y plus 4z. Let's look at exercise 4. We want to expand the expression from a product to a sum by removing grouping symbols using an area model and the repeated use of the distributive property. So let's take a look. So the repeated use of the distributive property. First, we'd write out the problem we have. Distribute the 3 to each item. So 3 is times x, 3 is times 2y, and 3 is times 5z. We multiply, begin the process of our multiplying. We get 3x, we get 6y, we get 15z, and that's our final solution for this expression. Let's take a look at the model. We would have 3 times x, 3 times 2y, 3 times 5z. Still get the same products, and the expanded expression is 3x plus 6y plus 15z. And for example 6. Example 6, a square fountain area with side length s feet is bordered by a single row of square tiles as shown. We want to express the total number of tiles needed in terms of s in 3 different ways. So let's take a look at some of those 3 different ways. First, let's move our shape over. And now let's take a look. So the first way, I could add all the s's together in 4. And the reason why we have a 4 is because there has to be a 1 foot by 1 foot in each of the corners. So there are 4 sides of s tiles and 4 extra tiles for the corners. The next way, I could write it as 4 times s plus 1. There are 4 groups of s tiles plus 1 corner. So we have 4 sides plus 1 for each corner. So we could do 4 times s plus 1. And another way that we could look at this is 2s plus 2 times the quantity s plus 2. It would still get us the same result. So there are 2 opposite sides of s tiles plus 2 groups of a side of s tiles plus 2 corner tiles. So these are just 3 different ways that we could write the expression for this problem. Ladies and gents, thank you so much for joining me with this lesson. If you have any questions, please bring them into tomorrow's class. Thank you.